Hello everyone. So today what I want to do is I want to teach you a general method for solving transient RL or RC circuits. And what I'm going to do is I'm going to go ahead and lay out an example, and then we'll just work through the general steps that we need to work through in order to solve the problem. So let's start with the following circuit here. We have a switch here and a capacitor. Another voltage source, call that V2, it's R2, R3, R1. And we'll go ahead and say that the switches from here to here at t equals 0. And what we want to find is we want to find the current through this resistor, IR1, as well as the voltage across the capacitor as a function of time. And the following values, we're going to use the following values here to solve this circuit. So V1 is equal to 6 volts, V2 is equal to 4 volts, R1 is equal to 4 ohms, R2 is 8 ohms, and R3 is equal to 6 ohms. So to solve this circuit, I'm going to lay out the general steps that you can apply for solving any kind of problem like this. So these are the steps to find any voltage or current in a transient RC or RL circuit. So the first step, step 1, is sketch out, or sketch, I'll just say sketch the circuit at t equals 0 minus, so right before the circuit switches, t equals 0 plus, right after the circuit switches, and t equals infinity, a long time after everything settles. Let's see, and find, so once you sketch out those circuits, you should find Vc of 0 minus, so the capacitor voltage, Vc of 0 plus, what the capacitor voltage is right after you switch it, and then Vc of infinity after a long time. And that's if you're dealing with an RC circuit. If you're dealing with an RL circuit, then instead what you want to find is you want to find the inductor current right before it switches, the inductor current right after it switches, and the inductor current after a long time. So that's for an RL circuit. Now, when you're sketching out the circuit at these different time periods, you have to go back to the fundamentals of capacitors and inductors when you're sketching these out. The first, when you're dealing with capacitors, is you have to remember that the voltage across the capacitor cannot change instantaneously. So the voltage across the capacitor right before it switches is always going to be the same right after it switches, always. So that means essentially that it acts like a voltage source during that brief time period. In a similar manner, when you're dealing with RL circuits, IL of 0 minus is equal to IL of 0 plus. So the current can't change instantaneously. So when you're writing out your circuit schematic for each time period, it's going to look like an open, or I'm sorry, a current source during that brief time period. Also, when you're sketching out these circuits of the different time periods, you have to remember that in steady state, a capacitor will look like an open circuit. And an inductor in steady state will look like a short circuit. So using these four basic principles, you can sketch the circuit at all these different time periods and then find out also what these relevant voltages are. So let's go ahead and apply this first step to our example here. So let's think about t equals 0 minus right before it switches. So right before it switches, this is connected and this is disconnected. If this is disconnected, this whole circuit here, it's only connected by this one wire, and so no current is going to be flowing here. So essentially you can disregard this whole half of the circuit when thinking about it before it switches. So essentially what the circuit will look like is simply just this circuit here. So let's go ahead and sketch that out here. So for t equals 0 minus, t equals 0 minus, we've got our capacitor here, our resistor R2, our voltage source V2, and then one thing we have to do is remember that in steady state, so we're assuming this circuit hasn't really been doing anything for a while, and then at t equals 0, it then switches. But before that, it's in steady state. So that means that this capacitor effectively acts like an open circuit. So you can go ahead and just put little open circuit terminals there. And then what we want to do is solve for Vc of 0 minus. So just looking at this circuit here, because we have an open circuit here, and there is no current flowing through this, right? There's no voltage difference across it. That means if you do KVL, essentially V2 is going to appear entirely across Vc. So Vc of 0 minus is just going to be equal to V2. And our V2 value is equal to 4 volts. Now let's go ahead and sketch the circuit at t equals 0 plus. So this is after it switches. So now it looks very different. Now the circuit switches, And so now this whole part of the circuit is connected, and then R2 and V2 are totally disconnected. So we can just disregard R2 and V2 and just draw this other half of the circuit. So we have V1, R1, R3, and that just connects directly to our capacitor here. There we go. So that's what it looks like now. But remember that the voltage cannot change in 0 time across a capacitor. So that means that Vc of 0 plus is just going to be the same as Vc of 0 minus, which is 4 volts. And as I said, basically during this brief switching period, it acts like a voltage source. So what you can do is you can go ahead and replace this capacitor with a voltage source of 4 volts. And that's what it looks like just at that instant right after it switches. So now what we can do, so we can now think about what the circuit looks like at t equals infinity. After a long time in steady state, we know that a capacitor eventually will look like an open circuit. So then the circuit will look like this. So that would be, the voltage here would be Vc of infinity. And you can see that this is actually just a simple voltage divider equation here. So Vc of infinity, that would just be V1, right, times R3 over R1 plus R3. And our V1 value is given as 6 volts. Our R3 value, 6 ohms. And then our R1 value is 4 ohms. So that gives you 3.6 volts. Okay, so we've done the first step. We've sketched out what our circuit looks like at these 3 distinct times, and we have found these capacitor voltage values. If it had been an RL circuit, or an inductor instead of a capacitor, then we would find these current values instead. It'd be a very, very similar process. So now let's go ahead and think about the second step with solving these problems. So step 2 is remove the capacitor or inductor, depending on what kind of problem you're solving, and find the Thevenin resistance looking into the terminals that the capacitor or inductor was connected to. So what you do is you take that inductor, that capacitor, you pull it out, and then you solve for the Thevenin resistance, looking into those terminals. Oh, and I should add connected to at t equals 0 plus. So this is after it switches. You want to look at the circuit after it switches. So let's go back then to this circuit here. So this is our capacitor. So what we want to do is we want to remove the capacitor, take it out. So let's go ahead and do that. So we have our V1, we have our R1, and then we have our R3, and then we want to remove this here. So we disconnect the capacitor, and then ask what R Thevenin is here. And basically you would just use the standard circuit analysis techniques that you were taught in some of the previous videos on how to find R Thevenin or Thevenin equivalents. You can see in this case it's pretty straightforward because we only have independent sources. What you do is you just turn off your independent sources and find the equivalent resistance. So if we short this V1, turn it off, you can see that R1 is in parallel with R3. So R Thevenin is just going to be equal to R equivalent, which is equal to R1 times R3 over R1 plus R3. And so you plugging that in, you'll get the numbers we have. You'll get 2.4 ohms. So that's the second step.
What do you got there? Oh, salami. Do you like salami? It's dead now. You can eat it. Oh.
So once we've done that, then we have the third step, which is compute the time constant tau is equal to RC in the case of an RC circuit, or, oh, and I should say R Thevenin times C, or tau is equal to L over R Thevenin. So in our case, tau is going to be equal to 2.4 ohms times, and let's see, I might have forgotten to give the capacitance value here. So C, I think in my notes I set C equal to, I set that equal to, it should be 0.13. C is equal to 0.13 farads. Actually in real life, that's actually a very large value, but for our example, it should be fine. So 0.13 farads. And that should give you 0.312 seconds for the time constant. So then once you've done that, we have the fourth step. Fourth step is that you want to find the capacitor voltage as a function of time, or the inductor current as a function of time, for t greater than 0. So if you're dealing with an RC circuit, you want VC of t. If an RL circuit, you want IL of t. So this would be for RC, and this would be for RL. And the formula that you use to, in general, find out the voltage or current as a function of time is this. So if you're dealing with capacitors, it would be this. VC of t is equal to VC of infinity plus VC of 0 plus minus VC of infinity. And that whole thing times an exponential e to the t minus t over tau. In the same way, if you're dealing with an R, so this is RC for an RC circuit. If you're dealing with an RL circuit, then you can describe the current through the inductor for after it switches as IL of t is equal to IL of infinity plus IL of 0 plus minus IL of infinity, all times e to the minus t over tau. And so you can kind of make some intuitive sense of this formula. Essentially, this infinity term represents the voltage that is due to an independent voltage or current source in the circuit. And we typically call this term here the forced response, because it has to do with an independent source that's driving the circuit. We call this term, this exponential term, the natural response, sort of that transient sort of voltage that's produced during the switching, but then it kind of settles down. And it kind of makes intuitive sense, right? You've got an initial sort of voltage here, and then you subtract the final voltage to get the magnitude of that transient, basically. And then this e to the minus t over tau term dictates how rapidly the signal or the transient dies off. So what we can do is we can plug and chug with this formula. Because we're doing an RC circuit, we'll plug it into here. So let's go to our example here. So VC of t is going to be equal to our VC of infinity, which we go back to that, we calculated that as 3.6 volts. So 3.6 plus our VC of 0 plus, which we go back, that was 4 volts, right? So 4 minus, again, the infinity voltage, which is 3.6, and then it'd be times e to the minus t over tau, which tau was 0.312. So that gives us 3.6 plus 0.4 e to the minus t over tau. So that describes, right there, describes the voltage as a function of time in our circuit. And that is what we wanted. One of the things we wanted to find was this capacitor voltage. Now, the other thing we want to also find, though, is we want to be able to find any sort of voltage or current in our circuit. So the way you do that, then, is the last step here. So the last step, step 5, use Vc of t or IL of t if we're dealing with an inductor to find any other current, or I'll say any other voltage or current in the circuit by replacing the capacitor with a voltage source of Vc of t or a current source IL of t. So that's in the case if you have an RL circuit. This is in the case if you have an RC circuit. So let's go ahead and do that. So if we want to find out, we're trying to find out this IR1 value, this current through IR1. And so what we're going to do, we're going to replace the capacitor with a voltage source here. So here's our circuit. We've got, here are 6 volts. We have our R1 resistor. And we have R3. And then we have our capacitor, but we're replacing that with a voltage source. And the voltage source is a value of Vc of t that we calculated, which is 3.6 plus 0.4 e to the minus t over tau. And so then we're wanting to find this current here, IR1. And so here now that we've just plugged this in as a voltage source, we can just use ordinary circuit analysis techniques then to find whatever voltage or current we want in the circuit. In this case, we're wanting to find IR1. So let's go ahead and do that just using basic circuit analysis. Because we know this voltage and we know this voltage, it should be really easy just to do a KVL loop, and then we can figure out what that current is. So let's go ahead and define a voltage here across the resistor. Call it VR1. And we know that we're wanting to find IR1, which is just VR1 divided by R1, based on how we assign the polarity there. And so then we just need to find what VR1 is. So we can do a KVL loop here. So KVL, going around the loop here we have minus 6 volts plus VR1, and then we hit a plus Vc. It's equal to 0. So then we can solve for VR1. So that's going to be equal to 6 minus Vc. And then just plugging that directly in, we know our Vc value is, we calculated that, so it'd be minus 3.6 minus 0.4 e to the minus t over tau. So there we have it. We've got the VR1 value there, and then we can just go ahead and divide it by R1 to get IR1. So IR1 is VR1 divided by R1, and our R1 value, what value was that? It was 4 ohms. So you divide that by 4 and you should get 0.6 minus 0.1 e to the minus t over tau. That's our answer there. So that pretty much wraps up the generalized method that you can use for any kind of first order RC or RL circuit. And yeah, it's very, if you follow these steps in a very systematic way, it's really hard to mess up. And again, with this last step, you basically just replace your capacitors or your inductors with voltage sources or current sources, and then solve the circuit like you would any ordinary problem. So I would recommend you just continue to work through examples and carefully go through these steps, and I think you will be in good shape. All right, I hope that was helpful. Thanks for watching, and I'll see you in the next video. Hello everybody, thanks for watching. If you found this content helpful, would you please consider liking and subscribing to the channel? That will help other people find it. And if you won't do it for me, will you do it for my cat, Muon? Named after my favorite subatomic particle, by the way. So, she will be very, very upset if you do not like and subscribe. So please, don't disappoint. How could you say no to this cuteness?